Hi, everyone, and welcome to day 3 of Qubits. Today, we have a set of 3 different tutorials where we're going to walk you through different aspects of programming using Ocean and our QPU, our quantum processing unit, as well as our hybrid solvers. So to get started, in this first hour, I'm going to take you through a basic example end-to-end of quantum computing and programming using binary quadratic models. In the next hour, Alex Kosegi, one of my colleagues, will take you through the constrained quadratic model, the new solver that's associated with that. And then in the final hour, we have a more advanced tutorial for dealing with large binary quadratic models and using NumPy and some more efficient Python packages to really help speed up the classical parts of your programs. So I'm Victoria Galieber, and it's really nice to have you all here. I'm a senior technical analyst on the European sales team based in Germany. So with that, let's just go ahead and dive right in with our first tutorial, quantum computing with D-Wave. So again, like I said, there's a beautiful picture of me, a senior technical analyst based in Germany. And for our agenda today, we're going to start just by diving right into a real world problem. We'll look at what is a basic problem that we want to solve. How can we formulate that as a binary quadratic model? What does an Ocean program look like to solve this problem? And then we'll run it live and wrap up with some Q&A at the end. So let's just dive right in and get our hands dirty with a real world problem. So let's start with a problem where we need to manage a set of pumps to satisfy daily consumer demand for water. This could be managing a reservoir and, keeping water levels steady so that we have enough water for all of our consumers downstream. We have 4 different pumps, as you can see in this table on the right, and each pump has a different cost to operate depending on what time of day we're going to use it. So for example, pump 1, P1, in the morning costs $36, and in the afternoon costs $27. Each pump also has a flow output, so a number of units that it can output at any given time. So for example, pump 1 in that far right column, you can see has a flow of 2. Now our objective is to minimize the cost to operate these pumps. And we have some constraints, like each pump needs to run at least once per day. We want to make sure for maintenance that each pump is getting a workout every day and none of them get rusty. We also have a constraint that at any time we can run at most 3 out of our 4 pumps. This is really in case one of the pumps that's being used breaks, we have a spare one to fall back on. And then last but not least, we need to satisfy this daily consumer demand. So in the bottom right of the table, you can see our demand is 20. We have a consumer demand of 20 units of water, and we need to make sure that our overall daily flow is going to be enough for that consumer demand. For this problem, if you wanted to solve this optimally, the solution would be a cost of $135. You can now see this table on the right. You can see which pumps we're going to run when. So in the morning, we're going to just use pump 2 for $56. And in the afternoon, we'll use pumps 1, 3, and 4. And now if you look at this, this is going to satisfy all of our constraints. Each pump is running at least once per day. At any given time, we're using at most 3 pumps. And if you add up this total flow, that's going to equal our consumer demand of 20. So now how can we formulate this as a binary quadratic model? This is really the native form that problems to run on the quantum computer need to be formulated as. Oops. So what does a binary quadratic model look like? Essentially, we need a minimization expression. So this is what we have here, where we have linear and quadratic terms. You can think about this when we think about the quantum processing unit, the QPU, as we have qubits. These are like our linear terms. And we have couplers connecting pairs of qubits. These are like our quadratic terms. And so when you look down at the hardware level, this is really what we have to play with in this binary quadratic model. Now, what we can control are the coefficients on these linear and quadratic terms. In this expression, those are the A's and the B's. We're going to choose values for these A's and B's to model our problem. so that when we go to minimize this whole expression, the minimum value will occur at our minimum cost. The Q's in this expression, these are going to be 0, 1 binary variables. And the quantum computer is going to tell us which values these Q's should take. Should they equal 0? Should they equal 1 to obtain that minimum cost? So again, we're going to choose the A's and the B's, and the quantum computer is going to give us back the values for the Q's. Now, how do we take this water flow and consumer demand problem and map it into this pretty simple expression? We've got a few steps that can really guide you through this when you're just getting started. So the first step, which we'll go through all of these together, is to just write out your objective and any constraints in your problem domain. This is like what you saw in the last slide where I said, our objective, we want to minimize cost. An objective is really something that you're looking to minimize or maximize. And then any constraints that you have for your problem, like every pump needs to run at least once per day. Those are all constraints that we need to satisfy. Once we have these written out just in words like we did on the last slide, we need to choose binary variables. So remember in that expression, those Q's, those were 0, 1 binary variables. So for this problem, we'll talk about what those binary variables should look like. Once you decide on those binary variables, we'll take those written objective and constraints and convert those to math expressions. These will be like equalities and inequalities using those binary variables. Step 3, we're going to modify our objective and constraints for that BQM form. So what you may have noticed in that equation is that it's one expression. So this is where we really need to combine these constraints that might be inequality statements or equalities, and we need to figure out how to wrap these up into one expression for the quantum computer. So what we really need to have is our objective written as a minimization function. And then we need constraints that are either linear or quadratic, equalities or inequalities. And we have some nice Ocean tools to help you deal with those and to help you build those into the BQM. Another option, which some of you may have seen in the past, is kind of rephrasing these constraints as a penalty model. So coming up with a math expression where the constraints are satisfied at their minimum value. And this method will absolutely still work if that's a method that you're familiar with. And last but definitely not least, step 4, combine your objective and constraints as a binary quadratic model. And this is really the easiest step. This is just really addition or using our Ocean tools to build these into your existing binary quadratic model. So when we formulate a problem as a binary quadratic model, or BQM, we have 2 forms that you can work with for our quantum computer and our Ocean SDK. So we have the QUBO form, which is where our variables take the values 0 and 1. And there's also the icing or the easing form, where your variables can take the value -1 or +1. Now, both of these are mathematically equivalent. So if you're familiar and comfortable working in one domain or the other, feel free to stick with that domain. And our Ocean SDK will even allow you to kind of switch back and forth and convert one to the other. So for this problem, we're going to use this QUBO form. My background's math and computer science. I'm always partial to the 0, 1 form. So that tends to be what I stick with. All right, so let's go through these steps for our problem. So we kind of already did the first step when we introduced what the problem was. So what is our objective? What are we trying to minimize? And in our problem with the water pumps and the consumer demand, we're trying to minimize our overall cost to operate these pumps for the day. What were the constraints that we have? These are like the rules that we need to satisfy for a solution to be feasible. So this problem, we had 3 constraints. The first, each pump runs at least once per day. The second, at any time, at most 3 pumps can run. And the third, that we need to satisfy that consumer demand for the day. So for this problem, step 2, we need to define our binary variables. And what I'm going to choose is we started with this table where we had, a row for each pump and a column for the morning and a column for the afternoon. And I'm going to assign a binary variable for each of these pump and time combinations. So we'll get a whole set of different binary variables. We'll have 8 for this problem instance. So we have, P1 in the morning, P1 in the afternoon, P2 in the morning, P2 in the afternoon. and so on. And what these binary variables will be are indicators for whether or not we should use the pump at that given time. So if a value of 0 is returned, sorry, I just noticed these are backwards. A value of 0 means that we will not use the pump at the given time. And a value of 1 means that we will use the pump at that time. So just flip those around from what you see on the slide. So when we get our solutions back from the quantum computer, if we get P1 AM equals 1, that means that we're going to use pump 1 in the morning. If you get back P3 PM equals 0, that means that we're not going to use pump 3 in the afternoon. So now that we have our binary variables, we can go through and define our objective and constraints using these binary variables. So for our objective, the words that we had defined on the last slides were minimize cost. So this is what we're really trying to do in this problem. Now, how can we formulate this using those binary variables? Well, we can look at the pumps, okay? So looking at these bullets on this list, so if a pump is used at a specific time, like in the morning, then there should be the cost to run that pump, whatever the assigned cost was. If we're not using the pump at a given time, then the cost to run it is going to be 0 because we're not using it. So basically what we want to do is take each of those binary variables and multiply it by the cost. Now, if we do this, then when we multiply a binary variable of 1, saying that we're going to use that pump times the cost, that gives us a value of cost to run the pump. If we're not using the pump, that has a binary variable of 0. And so that's going to zero out the cost that's the coefficient on there. So if we use these indicator binary variables, that's how we can really tell what this overall cost is going to be. And so here, sorry about the misalignment there, but this is going to be where our binary variables play a role. This 1 indicating that a pump is going to be used and a 0 indicating that our pump is not going to be used. So when we write this as a math expression, basically we have the cost to operate a given pump at a given time, cost PT, times the binary variable for operating that pump at the given time, XPT. So we have this for 1 pump and 1 time slot, and we're just going to sum up over all of the pumps over all of the time slots. And this is going to give us an overall expression for cost. And now the quantum computer is going to minimize this expression for us and give us back whether each of these XPT values should be 0 or 1 for the minimum cost. So what does that look like in terms of our table and our binary variables? Well, here you can see I have each one of our binary variables multiplied by the associated cost for the pump at the given time. So basically, we're just going to add up all of these red entries in this table, and that's going to tell us how much the cost is for the given assignment of binary variables. All right, let's dive into these constraints. So we have 3 different constraints, and the first one was that each pump should run at least once per day. Now, what does that mean? That means that if we look at a specific pump, the binary variable for running it in the morning plus the binary variable for running it in the afternoon should be at least 1. We want at least one of those time slots to be using the pump. And now, so that's for 1 pump. Now for our math expression, we can just sum up over all of the time slots if we had more than 2, which we just have 2 in this case. And we're going to have a different one of these math equations for each pump P. So for each pump, we have a constraint that it needs to run at least once per day. So if we go back to our table of these binary variables, this is like summing up these binary variables across the rows. So in the first row, we're going to add up the 2 binary variables for pump 1 and make sure that that's at least 1, that at least one of those time slots it's being used. And same for pump 2, pump 3, and pump 4. Now for constraint 2, we have that most 3 pumps can run at a given time. So now instead of looking at each pump's binary variables, we're going to look down those columns at the times. So for each time, let's say morning, we need that either pump 1 plus pump 2 plus pump 3 plus pump 4. That can be either 1, 2, or 3, or even 0, but it definitely can't be 4. right? We can't have all 4 pumps running at the same time. So this summation of these binary variables should be at most 3. For each time slot, in this case, we just have 2. We have the morning and the afternoon. So in terms of our table now, we're really summing up these binary variables down the columns, down each time slot, to make sure that each time slot, we have at least 1 pump available for use in case we need it as a backup. And then the last constraint, so we needed to make sure that our total flow satisfies that daily consumer demand. Now, this one, we need to look at what is the flow for each pump. And this is consistent for each pump over all the time slots. And so we're going to look at the flow times the binary variable indicator, is this pump used or not? And we're going to add up over all of the time slots, over all of the pumps to see what our total daily flow is and make sure that that equals our consumer demand. You could also use an inequality here if you wanted to make sure it was at least the consumer demand. I'm going to use an equality here just so that when we look at the code, you can see a little bit of the difference in what those look like. So if we look at our table, now you see I have each binary variable. It's multiplied by the flow for the given pump. And so this is how we're going to have that weighted sum of those binary variables. And in this case, we're going to add up all of these together rather than going across rows or down columns. We add everything together and we want to make sure that the total flow for the entire day is going to satisfy that consumer demand. In this case, the consumer demand that we had set was 20. All right, so what does this program look like? Let's look at some of the little code features that we've added into Ocean to help make this easier to code up for you. So first of all, for anyone that's brand new, how do we write a program for binary quadratic models? This is where our Ocean SDK or software development kit is really where getting started is. We're trying to make it as easy as possible. The majority of our Ocean SDK is open source and available on GitHub. So if you go to github.com/dwavesystems, you can go and look and take a look under the hood at, all of the methods that are being used for this, and almost everything is open source. We do also welcome community extensions, feature requests, bug reports, all of that through GitHub. So if you really feel like getting your hands dirty in that, feel free to go and dive in and see what we have over there. Now, at a high level, our Ocean SDK, this is an open source Python package. And so what this has is a lot of different resources and packages built into this one SDK. So starting at the bottom of this high level chart, we have compute resources. So we've got the quantum computers, the QPUs. We also have, hybrid solvers, and you may have CPUs, GPUs, or other compute resources at your disposal. And so what the Ocean SDK provides is a way to interact with all of these different compute resources, running binary quadratic models and also discrete and constrained quadratic models. So one row above these compute resources, you see the samplers line. And this is really like how you want to run and how you want to solve and optimize your problem. So we have our D-Wave API for running problems on the quantum computer. We have our different hybrid solvers and our hybrid solver service and our D-Wave hybrid package. And then we also have some classical solvers in there for you, like simulated annealing. All of these different solvers, when using our Ocean SDK, they work very well with our binary quadratic model, this method that we've been looking at today so far, as well as there's different solvers in the hybrid solver service for the discrete and constrained quadratic models. Now, on top of this layer, we have a row that says mapping methods. Now, these are for some more specific application domains like graph theory. So we have a graph mapping package called D-Wave Network X, which is really, really useful for working with some of those graph packages and those graph problems. And then up above that is really where you, the customer, the developer, this is where your applications would lie, sitting on top of our Ocean SDK. This is where you can build applications like portfolio optimization, traffic flow, nurse scheduling, that use our Ocean SDK to run your problems, your quadratic models on these different samplers and the compute resources underneath them. So there's lots of different packages in the Ocean SDK. I really encourage everyone to go take a look, dig around in there, as well as in our collection of examples. All right, so what do we need for our specific problem? For this water flow problem, what do we need to do? So first, we need to create a binary quadratic model object. So this is going to live in the DyMod package. We're going to import the binary quadratic model, and then we're going to build and initialize just an empty BQM. So there's nothing in here. I'm initializing this binary quadratic model, and I'm telling it that I'm going to use those binary variables, the 0, 1 variables. This is where if you wanted to use the Ising form, you could say, I'm going to use Ising -1, +1 variables. Next, we're going to build up this BQM one step at a time. So like I mentioned, when we talked about that Cubo development process, we really can just add these in one at a time iteratively. We don't need to worry about combining everything on paper or anything like that. We can build this up piece by piece. So let's start with the objective. We're going to build this by adding variables with a bias. So if you remember back to that binary quadratic model form where I said we have linear and we have quadratic terms, and we control those A's and B's, the coefficients. Those are the biases. So in this math expression, we have a summation where we've got linear terms. These those are our binary variables. So these are linear terms. And then our bias is going to be this cost. This coefficient, this is known to us. We know how much it costs to operate each pump at any given time. So we have our variable, we have our bias, and in Python, we're going to just add a variable for each of these with the given bias. So the Python form kind of matches the math form. So you have this summation. In Python, we have a for loop. So first, we're going to sum over the pumps. So our first for loop is for P in pumps. The second summation is over the time slots. So our second for loop is for T in time. And then we're just going to add these variables in one by one. So bqm.add variable, and we're adding this binary variable xpt, and the bias is this cost pt. Now what this add variable function does is it adds the variable if it doesn't yet exist in your BQM. If it does exist, it's going to add the bias to what's already there. So we're just iteratively building up our BQM. Next, we're going to look at the constraint 1. This was that each pump runs at least once per day. This was where we were summing over the rows in our table of binary variables. And we need to make sure that the sum of the binary variables for each pump P over all of the time slots is at least 1. So what should this look like? Well, in this case, our bias is just 1. Our coefficient is 1. We don't have anything really there. So that's just multiplied by 1. And our inequality has a lower bound of 1. And it has an upper bound. This upper bound should actually be 2 because we have 2 time slots. So if you think about this where we were summing across the rows, if both of the time slots we were using the pump, the maximum value it could take would be 2. And so this upper bound should be 2. Now in Python, this one does look a little bit more complex, but I'll step you through it. So again, we were summing, we had one of these constraints for each pump P. So we have a for loop for each pump in our list of pumps. And when we look at that summation that we had these xpt, those binary variables for the pump at the given times, and it had a bias of 1. So that's what you see in that line, C1 equals xpt, comma 1. This is just saying I'm going to use all of those binary variables for my pump over all of the time slots in time, and they each have a bias of 1. Now, one of the newer features that we have in Ocean, for those of you who have been using Ocean for a little while, we've added in this add linear inequality constraint function. Now, this makes it a lot easier for you who have been struggling to build and track those Slack variables that you had in your problems, and this is going to do all of that for you. So if you're new to Ocean and that doesn't make sense to you, don't worry about it. We've taken away all of that struggle for you. And so here we're going to add in a linear inequality constraint. And this C1, that is just the list of terms. So my binary variables with a coefficient of 1. My lower bound is 1. My upper bound, that should be the number of time slots, so length time, not pumps. We can add in a Lagrange multiplier, or Lagrange parameter, or penalty coefficient, whatever you're comfortable calling it. And then we're going to put a label in there for each of these constraints so that we can reference it. So if we just step through really slowly, so we have our bias. So in that math expression that we had, each one of those binary variables was multiplied by 1. We had our lower bound of 1. We needed that sum to be greater than or equal to 1. We had our upper bound, which should be 2. That was the total number of time slots. If we had them all turned on, if we had for that pump, we used it during every time slot, that would be 2. And then we have our constraint is added in. So now we can go to the second constraint, and this one is also an inequality constraint. So we'll be using the same function, but in words, we have at most 3 pumps can run at a time. So our equation we had for each time slot, we were summing down the column. So over all the pumps, we're summing up the binary variables, and that should be at most 3. Now, one thing that you'll see in some of these functions is a lot of them are set up so that you just have a 0 on the right-hand side of the expression. So if I just move that 3 over, subtract 3 from both sides, then I get an equivalent math expression where I have the sum over all of the pumps minus 3 has to be less than or equal to 0. For each time slot t, I'm going to have one of these expressions. So we have a bias of 1 again, and we have an upper bound of 0. And in the code, we have a parameter called constant. This is when we move it over and our upper bound is 0. This constant now is -3. And you'll see where that comes in. So now in the code, we are summing for each of the time slots, we're summing up over all of the pumps. So here for constraint 2, I have a list of terms C2. Each one of them has a bias of 1. And I'm going to use this add linear inequality constraint again. I'm going to add up all of those terms. That constant was -3. Again, I can have a Lagrange multiplier or Lagrange parameter, and I'm going to give it a label. So we have a bias of 1. Our constant of -3. So when your upper bound is 0, you've got a few more options. You can do it in a much more simplified manner, or you can choose to use that lower bound and upper bound feature. And then the last constraint, this was our equality constraint, where the total daily flow needs to satisfy that daily consumer demand. This was where we were summing up over everything in our table. And so again, what I'm going to do is move that constant over to the left-hand side. Demand was a constant. That was an input to the problem. We knew the consumer demand was 20. So if we move that over so that we have a 0 on the right-hand side, it's going to take a really similar form to what we just saw with that linear inequality constraint function. So here we have our coefficients or biases are these flow numbers. Those were input. We had all of that information when we got started. And so those are going to be our biases in that summation. So bias of flow, and our constant is going to be negative demand. Now, if we go over to the code, here we're going to see a really similar thing where we're summing up over all of the time slots over all of the pumps. We're adding up everything that was in that table. And we have our bias, which is this flow value. And we've got, again, our binary variables. And then here with this add linear equality constraint, I'm going to use that constant equals negative demand. And again, I can put in a Lagrange multiplier or a label if I want to. So lots of different functions here to help you build up that binary quadratic model so that you don't have to do all of that math and converting that we used to have to do. So now I'm going to go ahead and share my screen and we'll do a little demo and run this live. So let's get this started. It looks like my screen sharing is disabled. Can the Pathable team enable screen sharing, please? Thanks. All right, so there we go. So hopefully everyone can see my screen now. And what I have open here is in our Leap IDE. So I have written up a short little code, a little program in Python using our Ocean SDK to run this problem that we just talked about. Let me make this a little bit bigger so that you all can see. All right. So as any good Python program begins, we import a bunch of different packages. I'm going to run this on the quantum computer in Canada. So I'm going to import the D-Wave sampler for that. And then we're going to build up our binary quadratic model. I'm going to first set up my scenario. This is all of those inputs that we had. What pumps do we have? How much does it cost to operate each pump? What sort of flow does each pump have? What is that consumer demand? And how many time slots do we have? Next, I'm going to build up a variable for each pump. This is just a list of strings of what I'm going to call each of those variables. So just like we had in the table, you'll see like P1 AM, P1 PM, and so on. Next, we're going to initialize our binary quadratic model and tell the BQM that we want to use binary variables. And then we just dive right into building up our BQM. So this is the same code snippets that you just saw on the slides where we stepped through everything one by one. I'm going to build up my objective. So I'm going to add a variable and assign a bias for the cost because we want to minimize cost. I'm going to add in my first constraint where every pump runs at least once per day using that add linear inequality constraint function. I set the lower bound, I set the upper bound, I set a Lagrange multiplier, and then I added a label. Next, for constraint 2, at most 3 pumps per time slot. This is where I used that constant option where I moved that number over to the left-hand side so that my upper bound was 0. And then the third constraint, this was satisfying our daily demand. This was where we used the add linear equality constraint, and our constant was this negative demand. And again, we have a Lagrange multiplier. Next, I'm going to define my sampler. So I'm going to run this on the quantum computer. So I'm not going to use one of the hybrid solvers or anything. We're going to run this directly on the quantum computer. And so when you run problems directly on the quantum computer, we're going to use the embedding composite as well and allow the Ocean SDK to figure out where and how to fit our logical problem onto that physical chip structure. So I'm going to define my sampler, and then I'm going to sample my binary quadratic model. Since the QPU is probabilistic, I'm going to run this problem 1,000 times. Sounds like a lot, but you'll see how fast that really is. Everything down here is really just processing what the solution returned is. So I'm going to get back binary variable values that are going to say like P1 AM equals 0, P3 PM equals 1, and things like that. And so we'll have a nice printout on the terminal. So now in the Leap IDE, everything is already installed for Ocean, and it's already linked to my Leap account. So what I can do is just up here in the top right, click this run button, and the code should all run right out of the box. A terminal will pop up, and it should run my problem, and there we go. So I know I told you 1,000 runs wasn't going to take a long time, and I told you in the beginning I live in Germany, and this ran on the quantum computer in Canada, in British Columbia. And so the solution that we got back, this is just like that table of variables that we saw where we have a row for each pump and a column for each time slot. And it's telling us that for pump 0, we're going to run that one only in the afternoon. And pump 1, we're going to run that only in the morning. And then 2 and 3 will be in the afternoon. We'll get a total flow of 20, which is going to satisfy that consumer demand. And our total cost is $135, which we saw way back in the beginning that was the optimal cost. So what we have also, if you're interested in learning more about an example that's similar to this one, is this is actually a fork from GitHub of one of our code examples. So what I did was over on GitHub, you can click the fork button and fork it to your personal repo. You can make changes and do whatever you want. But this is from our reservoir management code example. So this is a new code example where we're looking at managing water levels in a reservoir. So again, we have some consumer demand. We have pumps that we can choose to turn on and turn off. But we also have additional constraints like the water level can't go below a minimum value. The water level can't go above a maximum capacity value. And we also have a lot more time slots. The costs fluctuate throughout the day because power costs fluctuate throughout the day. So it's a much more complex version of this simple example that we just saw. I'm going to show this to you and run this on the hybrid solver. So here, this is straight from the collection of code examples. So if you go to github.com/dwave-examples, or in Leap, if you click the resources button, you should find the collection of code examples. Now, this is going to use the binary hybrid sampler, so our original HSS solver for binary quadratic models. It's going to have a similar kind of structure where we're going to build up the binary quadratic model based on all of the inputs that we have, like flow and demand and things like that. We're going to build up each of our things iteratively. So we have an objective. We've got a constraint 1, constraint 2, constraint 3. So a lot more complex than what we just saw, but it's going to run pretty quickly too. So let's go ahead and run this. And this is going to run on our hybrid solver. And so it already built the binary quadratic model. And now it's running our hybrid solver to solve this scenario. Now this, like I mentioned, there's a lot more time slots. So it's a little bit harder to read because I've zoomed in on my screen. But you get the same sort of printout where it tells you which pumps should run at which time of day. There's 24 different time slots. You can check the water levels at any given time slot to make sure it's within those allowed values. You can look at the total cost and the total flow. And it's also going to build up a nice animation. So once the program's done, you'll see this reservoir.html. And I'll just click open with preview. And we should get a nice little video of our solution like what you saw in the README. So here, we'll just run it once and I click play. And you can see this is the solution that we just found. You can see the cost for each hour. So when it's more expensive, when power and electricity is more expensive, we're not going to run any pumps. And when it's cheaper, we're going to build the water levels up a lot higher to prepare. All right, so let's go back to my slides. And we'll take a look at that more complex demo a little bit more in depth. So as I mentioned, I ran this through Leap, and Leap is our cloud service. Anyone can go and sign up for free if you're in one of our Leap countries. There's tons of resources there, and you get access to a whole bunch of different solvers and hybrid solvers, as well as interactive demos, code examples. There's just tons of resources there. I think you can also get a free t-shirt if you go post in the community. So I encourage everyone to do that. Now, the small example that we ran, so this looks really similar to the solution we got. It's a really small problem, so I'm not surprised that we got the optimal solution and that we got everything back. But yeah, so we got the optimal solution running live on the quantum computer just now. And now this more realistic and complex example that I shared with you. So again, you can read all the details on this in the collection of examples, but here's what it actually was running. So again, our objective was to minimize overall cost, but here cost is a little bit more complex. Rather than having a fixed cost for each pump over any time you want to use it, cost here is a function of how much power is required and what the power rates are at different times of day. So getting much more realistic to building up that more real world application. Now for the constraints we have, again, each pump needs to run at least once per day. We want each pump to get a workout every day. We don't want anything getting rusty. And again, we have the same second constraint that at any time we need at least one pump free as a backup. So really important that if a pump goes down, we can still satisfy consumer demand and we're not depleting our water supply. And then the last constraint, this is the new one that's a lot more complex, where we have a starting reservoir level and we have a minimum and maximum allowed levels. And we need to make sure that at any time during that time of day that the reservoir level is within that specified range. So you need to balance the flow in from the pumps and the flow out of consumer demand for each hour rather than for the whole day as we did in the simple example. And so this gets a lot more complex. This is based on a paper from 2021, so this year, that is looking at how you can formulate some of these more realistic water reservoir management problems and applications as binary linear programs. And then I just took that and threw it right on our hybrid solvers. So once you have, this binary formulation using the Ocean SDK, it can be pretty easy to get it all set up and running once you have some practice. All right, so just to wrap up before we open it up to Q&A, so we've got lots and lots of different applications. So this water management one that I shared with you, this is just one application that I implemented based off of this paper. But we have lots and lots of customer use cases and real world applications if you look on our website and look at the applications area. So just dwaveassist.com/applications. We also have tons of resources in LEAP, but I also want to make sure that everyone's aware of the resources that we have outside of LEAP. So, even if you can't sign up for a LEAP account, you can still explore different resources that we have for both executives and developers. We have tons of videos on our YouTube channel. We have white papers describing, our current offerings. And we also have getting started guides, like there's one that's Ocean Programs for Beginners. There's another guide on formulating your problem as a binary quadratic model. And so I really, really suggest everyone to go take a look at what's there as well as what's inside of LEAP. Next, everyone should go sign up for LEAP. It's free. You can play around. You can run all of these demos that I just showed you. And then definitely last but not least is our new Developer Champion program that I hope you all heard about yesterday from Nikhil. All right, so with that, thanks for your time. And Susan, do we have any questions?
Hi, everyone. Thanks, Victoria. We do have a lot of questions that came in. Some were answered during the chat. We do have some experts online. If you have some additional questions, please put them in and I'll try to read them before we go on to the next section. One question we got a lot was about the recording of the session. So all of the sessions from the tutorials today and the last 2 days will be available back on the Pathable platform. It'll probably take us another day or so to get them all loaded, but they will be on Pathable for about 3 months. So you can go back in and any sessions that you missed, you should go back and take a look. Ultimately, we hope to put all of these out on the D-Wave YouTube channel, which also has a lot of other information, tutorials, webinars, etc. So just a great wealth of information in addition to the resources on Ocean on GitHub and LEAP. We have a couple of questions here, one of which we seem to get all the time, which is how do you calculate the Lagrange parameter?
Yeah, so that's actually a really good question. And what I usually do is it's guess and check. So it's a little bit of trying different values, running your problem and seeing what comes back. Essentially, you need to balance those coefficients and the outputs from the objective and the constraint portions of your problem. It can be tricky, which is one of the benefits of our new constrained quadratic model hybrid solver, which Alex is going to talk about next. So in the CQM solver, it's going to handle all of that for you. So if that's something that you're really struggling with in your problem, I would strongly suggest that you go try out the CQM solver and see if that helps. Unfortunately, there isn't really like one good answer to tell you like you should always use this number or anything. It's really going to depend on your problem, and it's really going to be kind of like a grid search, similar to how you would tune parameters in like machine learning algorithms and things like that. You're going to try different values, check out the results, and see which ones are the best fit.
Okay, and a corollary, and perhaps you answered this, but I'll ask anyway. While defining the cost function, do we need a Lagrange parameter?
So for the cost function, I did not have one in mind. So for my objective function, I did not put a Lagrange parameter. You can if you want to, but it's actually equivalent to, you can leave one of them as a value of 1, and then everything else is kind of relative to that. It's explained more in Andrew Lucas's paper. If you haven't seen that paper, that's a really great one. If you just do a search on Google for Andrew Lucas, Ising forms for NP complete problems, it'll come right up. But basically, you can have a Lagrange parameter in front of everything if you want to, or you can set a 1 in front of one of them, and then everything else is relative to that one.
Okay, someone asks whether these code examples can be run on Amazon Braket.
So unfortunately, the reservoir management code example that I just shared, that uses our hybrid solver. And unfortunately, through Amazon Braket, you only get access to the hardware, to the QPUs, and not the hybrid solvers. So if you wanted to run that on Bracket, you would need to swap out for one of the QPUs. Since it's a binary quadratic model, it should be fairly straightforward to do that. You would just want to make sure that there weren't too many variables for it, but I think for that problem, it shouldn't be too bad.
Okay, and one last question before we move on to Alex. Have linear and quadratic gone away, or are these additional ways to add to the BQM?
These are additional ways to add to the BQM. In my talk that I'll do after Alex's, where we talk about using NumPy to efficiently build binary quadratic models, I will go back to that linear and quadratic form. Those are still there. You can still set those. You can still use a matrix form if that's what you're comfortable with. This is just making it a little bit easier so that you don't have to do all of that algebra yourself.
Okay, well, we have a few more questions that came in. Would there be any way to see the final QUBO or know how many total variables are utilized? Mainly, as the number of variables increase, will the num reads of sampling need to be increased?
Yes and yes. So you can see at any point, you can see what the binary quadratic model is. You could just print that out and it's going to give you what are the linear terms, what are the quadratic terms. So I could do that, at each stage of iteratively building up my BQM, or I could do that at the end and I can see, okay, these are my linear coefficients, these are my quadratic coefficients. There's also information fields like variables, so you can print out a list of all the variables in your BQM. And then what was the last question again?
As the number of variables increase, will the number of num reads of sampling need to be increased?
Yeah, I would guess so. Yeah.
Okay. And someone else asked, why do you run the code 1,000 times? Was the result an average of those runs?
So I ran the code 1,000 times just to make sure that I got the optimal solution. I could run it 10 or 100 times and I'd probably still have a good chance because it's a small problem, but I didn't want to risk it in front of a live audience for you all. So I ran it 1,000 times just to really make sure that I got the optimal solution. It's not an average of the different runs. It's actually pulling the best answer out of all of those runs. So it's going to take all of those 1,000 solutions. Some of them are going to be repeats. And I'm going to say, okay, give me the very best one, which is usually going to be like they're ordered. So the best one is usually first. And so that's what we really looked at was out of those 1,000 reads, what was the best solution that you found?
Okay. And the last question we're going to take before we move on, how to access and run the code. Can we run the code by installing dwave.system on our computer, like running Qiskit from VS Code?
Yeah, so to run the code, so the code is on GitHub at dwave-examples. It's the one called Reservoir Management. You can run it, like I mentioned, and like I did, you can run it right out of the box in the Leap IDE, or you can run it locally on your computer in your terminal or your command prompt. You could install just like the necessary packages, but I would suggest that you install the whole Ocean SDK. So that you can just do with pip install dwave Ocean SDK. And there's full discussion and description on how to do that in our documentation.
All right, well, two more good questions just came in, so I'm going to go with these and then we're going to cut it off. But we will have another Q&A session after Alex. And as I said, we have experts in the chat, so feel free to continue having those questions come in. Question is, how many qubits are we using? Is there a way to know the running time and the quantum computer behavior?
So I think it was shown in some of the talks yesterday, the problem inspector. You can really, in the IDE or running locally, you could use dwave's problem inspector to see exactly how your problem was embedded onto the physical chip. And you would get a nice picture and mapping from logical variables to qubits on the physical QPU. So that's a really nice visual way. Or if you wanted to actually see, you can get all of that information from those embedding tools that I mentioned. You can get the embedding returned, you can analyze that and see exactly which qubits your variables were mapped to.
All right, and the final question, and then I'll ask our experts in the chat to go in and answer some of the others. Now, of course, it's gone up the screen here. Is there any way to know if you have the optimal solution?
So, I mean, it would really depend on if you know the optimal solution to your problem going in, right? So just like with classical heuristic or probabilistic methods, There aren't really guarantees unless you have like a theoretical bound on your problem that you can get that guarantee. It's a probabilistic system, and so you're getting this distribution of samples back. But just like with classical algorithms that are heuristic or probabilistic, no, there's no guarantee.
Okay, well, with that, we're going to move on to the next part of our tutorials. Thanks, everyone. Keep the questions coming. Thanks, Victoria.
Thank you.
Hi, everyone. Thanks for joining us for the tutorial sessions this morning. I hope you enjoyed Victoria's. I always enjoy listening to her. She is definitely an expert at D-Wave. I'm Alex Kasegi. I'm a technical sales engineer at D-Wave, and we'll be talking to you about the CQM model and the CQM hybrid solver today. So by now, you've probably heard quite a bit about the CQM solver. It's our latest hybrid addition to our hybrid solver service. We introduced it on Tuesday, and Hussein gave a great talk yesterday explaining the benefits of it. So there we go. Like I said, I'm Alex Kasegi. Okay. So today, in this tutorial, we're going to take another look at the CQM model and the hybrid solver. I'll just give kind of a quick high-level overview of it so that we're all on the same page about what it is and why we might want to use it. We'll then take a look at an example. So I've chosen the delivery truck packing problem, actually inspired from a customer conversation. So we'll take a look at how you might formulate this problem using a CQM and then submitting it to the solver. So I'll run a live demo, the same as Victoria, so you can see the solver in action. We'll then just summarize what we learned, and I have a slide to direct you to other code examples that use the CQM solver that you can explore if you're interested in continuing on. All right, so first I want to start by just quickly talking about our hybrid solvers in general. So we designed our hybrid solvers really with business applications in mind. They're designed to work on enterprise scale problems, and they use classical and quantum resources to solve industry size problems. The binary quadratic model solver was the first hybrid solver that we introduced. It can work on problems with up to 1 million binary variables. And the discrete quadratic model solver was our second addition to the hybrid solver service. It was also our first expansion into new problem domains. So this solver can work with discrete variables. Like Alan said on Tuesday, discrete variables can take on a value from a set. So for example, if I have a set 11, 19, and 29, then a discrete variable could choose one of those values. Discrete variables can also choose from colors, from strings. It's really up to the user to define. It's worth noting that the binary quadratic model and the discrete quadratic model solvers, they support unconstrained problems. So they work on unconstrained problems. The constrained quadratic model solver, like you saw on Tuesday, is our latest addition to the hybrid solver service. And as Hussein said yesterday, the constrained quadratic model solver really is the best choice for constrained problems, which are pretty much all industry problems. Additionally, the CQM solver works on integer variables as well as binary variables. So now we can construct models that have both integer and binary or just one of the other. So this is our first kind of expansion into the integer domain. With the latest release of Ocean, so Ocean 4, I believe 4.1, we've also introduced tools that help with more intuitive formulations for constraints and objectives. So this means that it's easier to take your mathematical formulation and translate it directly into code. And you'll see an example of this in our delivery truck packing example. The CQM model, at least the enterprise version, can work on problems with up to 500,000 variables. If you sign into Leap right now, you'll notice that the CQM solver works on problems with up to 5,000 variables. A range of 750 million to 2 billion biases, and it supports up to 100,000 inequality and equality constraints. Now, I'm not going to go through this table in detail, but I just wanted to point out that the BQM, DQM, and CQM solvers, they all have different kind of properties, and they're all useful in different cases. So the CQM, like we've said, is really the best choice for any constrained models that you're working with. The binary quadratic model solver is still a really good choice for naturally binary quadratic models. You'll see that each solver supports a different number of maximum variables. It's worth noting that the BQM does support a larger number of variables, but if you were to take a DQM or CQM model and formulate it as a BQM, you would require more variables. So it's not a direct apples to apples comparison here. We'll also see later in the example that the CQM solver, in terms of solutions returned, is similar to the DQM in that it returns the best solution found, as well as a number of intermediary solutions, which can be helpful for comparison. Oops, wrong one. There we go. Okay, so before we get into the code example, I wanted to point out a few kind of features or highlights of the hybrid CQM solver. So when I first was introduced to this solver, I found that there were these kind of five highlights that are most noteworthy, I would say, compared to the other solvers that we have available. So the first, and I've mentioned this before, is that the CQM solver supports multiple variable types. So binary types and integer types. The second is that with Ocean now, we can represent objectives and constraints in a really kind of natural and intuitive way. So this will speed up that process of going from problem formulation to programming and essentially developing a POC. So we are supporting you to go through that process a lot more quickly by allowing, by supporting you with more tools. The third feature or highlight is that the CQM solver has native hard constraint handling. So with that, we're also able to add soft constraints to models. This is the first time that we're able to really distinguish between hard and soft constraints and how we handle them and how we add them to a model. So that's a new feature, and yeah, so that's a new feature of the CQM solver. The fourth highlight is that the CQM solver returns solutions that include information about which constraints were satisfied in the model and overall solution feasibility. So we'll likely get feasible solutions, but we may also get some low energy infeasible solutions that we can drill down into to see which constraints were satisfied and which weren't, which can be really useful information for us to have. And the last point, and there was a question about this at the end of Victoria's talk, was that the CQM solver now auto-tunes Lagrange parameters. So Lagrange parameters, like you saw, are the weights on the constraints. If you choose to use the CQM solver, you no longer have to worry about tuning those Lagrange parameters yourself. So now we do that for you. With that, it's worth noting that the CQM solver does tend to take a bit more time than the BQM or DQM solvers. However, in the long run, it's still much more efficient to use the CQM solver because you don't have to manually tweak the Lagrange parameter, resubmit the problem, and continue to iterate on that process. We handle that all for you. So that's a huge benefit of using the CQM solver as well. Yep. All right, before we dive into the example, I want to just talk about some of these features in a little bit more detail because they're really foundational to using the CQM solver. So I mentioned a few times now that we support binary and integer variables, we now have to define these binary or integer variables explicitly, either by adding the variables to the model, as Victoria demonstrated with the BQM, or by using these new objects in Ocean called binary and integer. So in the first example at the top here, we're defining a binary variable, x. What this is doing is this binary constructor here is creating a binary quadratic model that contains a single variable with the label x. So x is in parentheses there, and that indicates that it's a label that's added to the BQM. Likewise, when we construct an integer variable, this integer constructor here will create a quadratic model that has a single integer variable within it. In this case, the integer variable is labeled I and has a linear bias of 1. Once we have binary or integer variables defined, we can then use symbolic math. So that's that new, more intuitive way of constructing objectives and constraints to build objectives and constraints. So in these examples here, the x, I'm just going to say the x's refer to a list of binary variables. And in the constraint section, the capital I is going to refer to a list of integer variables. So if we look at the objective box, that first box on the slide, you'll notice that we're defining the objective using the sum function in Python. So what's written here is pretty typical of any objective. What we're doing is we're multiplying some weight by each of the binary variables and adding that all up. So we're going to want to minimize the sum of that quantity. What we used to have to do is use a for loop to iterate through all of the variables and add the weights to the binary quadratic model or the Cubo dictionary. But now we can just use built-in tools in Python or an optimized version of sum called QuickSum that we provide in Ocean to much more easily add up these variables and construct these objectives. Once we have an objective, we can add it to the CQM. I actually have a typo here, so that should be CQM.setObjective. In my subsequent slides, I do have the right function, so just make a note of that. And to build constraints, this is really where symbolic math shines through and makes our lives a lot easier. You'll notice that in the second box, I'm defining an equality constraint and an inequality constraint. So for the equality constraint, I'm summing up a list of integers, so a list of I, that's going to be integers, and I'm using the equality operator to set it equal to 50. If you've worked with our systems before and used equality constraints before, you'll remember that you've needed to use a nested for loop to add linear biases and quadratic biases to the model. So you can see how convenient it is that, you can see how convenient it is that we can just replace that nested for loop with a single line. Likewise, for the inequality constraint, we can use the summation function again. Here, what we're doing is pretty typical of any constraint. We're multiplying some cost by a binary variable, and we're adding that up for all the binary variables in the model. In this case, we're going to use the inequality operator, less than or equal to, and we'll choose 500 for this inequality constraint. It's just an example of what we could do. But you'll notice that this single line of code now replaces the need to add linear biases, quadratic biases, and slack variables to the model to represent the inequality constraint. So this is what I mean by this more intuitive way of programming our models can really help us speed up the time to go from problem formulation to proof of concept. And it can also help reduce the chance of error as well. To add constraints to a CQM, we just use the add constraint function as shown in the bottom box there. All right, the last point I want to touch on before we dive into the example is this idea that we can distinguish between hard and soft constraints now. So all constraints that are added to the model, like we saw in the previous slide, through that add constraint function, are considered hard constraints. So what that means is that they need to be satisfied in order for the solution to be considered feasible. We can still add soft constraints to the model, though, if we want to. And the way we would do that is just through the old way. So we would construct a penalty model, and instead of adding it to the constraints, we would add it to the objective. The box here is one example of a penalty model for an equality constraint. So if we wanted to add that soft constraint, we would multiply it out and add it to the objective the way we're used to doing. All right, so now let's take a look at an example. So in North America, there are over 100 standard box sizes that consumer goods are shipped in. So think about when you order things from Amazon or maybe Walmart or Costco, often you probably receive things in different sized boxes. So there are a lot of different standard size boxes. And the problem of figuring out what boxes to pack onto what trucks and how to optimally pack those boxes so that you're filling up as much space as possible within the truck is a very difficult combinatorial optimization problem. It becomes even more difficult when you start to consider things like priority shipping. So did a consumer or did a customer pay for priority shipping, or did they just opt in for standard shipping? If we consider things like customer satisfaction as well, we might be concerned about the transit time of the package. So we might want to minimize the number of days that the package is on the road between the time the order was placed to the time it's delivered to the customer. So all of these additional considerations can make for a much more complex model. We're going to look at a simplified version of this in this example. So we're just going to consider a single truck. We're also only going to consider a single package size. That way we know how many packages can fit in the truck and we don't have to think about orientation, like in a 3D bin packing problem. It's a lot more simple to just consider one package size. So we'll just do that for the sake of this example. We also want to make sure that people who have paid for priority shipping, that we're prioritizing getting their packages onto the truck. And we want to minimize the number of days that pass since an order was placed. So orders that were placed longer ago are going to be prioritized to make it onto the truck. The truck is going to have a weight and a size capacity as well, and we can't exceed those. Okay, so the CQM development process is very similar to the BQM development process that Victoria went through. We're going to start by writing out our objective and constraints in the problem domain, then defining our variables. Then we'll convert the objective and constraints to math statements. And after that, we can program the CQM model in Ocean and submit it to the hybrid solver. All right, so for this example, we're going to have two objectives and two constraints. The first objective that we're going to consider is that we want to maximize the number of packages selected that have priority shipping. So if people pay for priority shipping, we want to make sure we're maximizing those packages. We also want to minimize the number of days that each package is in transit. Then our constraints are that we need to make sure we don't exceed the maximum number of packages that can fit on the truck. So for this example, we're just going to say that's 100. And the second constraint is that we can't exceed the maximum weight capacity of the truck. We're just going to arbitrarily choose that to be 3,000 pounds. All right, now the second step is to define our variables. Since we want to make a decision about whether or not we're loading each package onto the truck, that's a binary decision. So either we load it or we don't load it. We're going to use binary variables. And we're going to use one variable per package. If the variable is equal to 1, we're going to say that we're choosing that package to load onto the truck. And if it's equal to 0, then we're going to leave the package behind. Okay, now we're going to define our objectives and our constraints mathematically. So the first objective is to maximize priority shipping. The way we're going to do this is by using a value P. P here is going to indicate the priority of the package. So a higher value of P is going to indicate a higher priority package. A value of 1 is going to indicate just standard shipping. So we're not going to prioritize those packages as much. So each package X is going to have its own priority associated with it. And since our hybrid solvers, like our QPU, naturally minimize quantities or functions, we are going to multiply this by -1 to turn it into a minimization. Oops. The second objective is that we want to minimize the wait time. So here we're going to use this value D. D is going to indicate the number of days that have passed since the order was placed. So a higher D is indicative of a package that we want to prioritize. So if 5 days have passed, we want to prioritize the package that has been in transit for 5 days over a package that's only been in transit for 1. Again, we need to turn this into a minimization, so we're going to multiply by -1. The first constraint that we're going to consider is this maximum parcel constraint. So we said that the truck we're considering can only fit 100 parcels on it. So we want to make sure that we select, in this case, I'm going to say exactly 100 parcels. I want to pack that truck completely full. And I also want to show how to kind of program and work with an equality constraint. So here we just have to add up the packages that we've selected and ensure that it's equal to the maximum number of packages that the truck can fit. All right, before we move on, I just want to take a moment to flash back to how we used to handle equality constraints. So on the left-hand side here, we can see that once we have our math expression for this equality constraint, we have to do some manipulation before we're able to program it. So in order to build a penalty model out of this, we have to move everything to one side, as you see in the second line here, and square it. After that, we have to expand all of the terms and then collect the terms. And what we get is an expression that has 1 minus P as the linear bias and 2 as the quadratic bias. So at that point, we could then add the linear biases and the quadratic biases separately to the model. Now with the CQM though, once we have that math expression, we can just go directly to programming the constraint. So we don't have to build out that penalty model anymore. And the way we would program the constraint is shown here on the right. So the equality constraint here is going to use the quick sum function. So that's the optimized sum function that we've created. It lives in DIMOD. So we're going to use quick sum to just sum up all of the binary variables. So the xi is going to be a list of binary variables like we saw earlier. And we're going to use the equality operator to set it equal to the maximum number of parcels, or P. The second constraint that we're considering is the maximum capacity constraint. So for this constraint, we need to make sure that the total weight of all the packages we select is less than or equal to the payload of the truck. So in this case, we decided that capital W here would be equal to 3,000. Okay. Now, again, before we move on, I just want to take a look at how we used to deal with inequality constraints. On the left-hand side here, I've shown how we build a penalty model. So note that it's similar to the equality constraint in that we have everything on one side and we square it. However, we also need to introduce slack variables, which are represented by that expression for Z. So in addition to the binary variables that we have for each package, we also need to introduce log W slack variables to make sure that the inequality constraint works out. So I didn't even bother expanding that. It's just a little too complicated, but I think you understand that it's a bit of a pain to expand out the inequality constraints and add that to a model. So on the right-hand side, what I'm showing here is that, again, we can bypass all of that work. As soon as we have a math expression for our inequality constraint, we can add it directly to the CQM, or we can define it directly. And again, we're going to use the quick sum function. We'll multiply the weight of each package by the binary variable for the package. So the binary variable is X there, and use the inequality operator to set that as less than or equal to the maximum weight. So much quicker and a much easier way of getting from that math statement to the code. Okay, now that we have expressions for our objectives and constraints, we can program this up in Ocean. So we'll start by instantiating a constrained quadratic model, and then we'll add the objectives and constraints to it. To instantiate a constrained quadratic model, we're going to import the object from DIMOD, as is shown, and then we can just call the constructor. So the same way as how we'd create a binary quadratic model, just with a constrained quadratic model. Next, we need to create our variables. So we've already seen that we can use this function called binary. What I'm showing here is that we can create a list of binary variables. So what I'm going to do is create a list that has one binary variable for every item or every package that we're considering in the model. Next, we can add the objectives to the CQM. So the first objective is shown here. This is the priority shipping objective. Victoria mentioned in her tutorial that we can add weights to objectives. And so I'm just showing that here for illustrative purposes. The objective weight priority is the weight that we could set on this objective if we wanted to. And then we're multiplying it by the objective itself. So summing up the priority of each package times the binary variable for each package for all items that we're considering. For the second objective, again, I'm showing a weight that's optional depending on your application, and then multiplying the weight by the objective itself. So here we're summing up the number of days that have passed since an order was placed on a package times the binary variable for that package, and we're doing that for every package that we're considering. Then to add objectives to the CQM, notice in the last line, we're using the set objective function, and I'm adding both objective 1 and objective 2 together at the same time when I use set objective. This is important because set objective will replace the objective that's already there. So if you have multiple objectives, you'll want to add them all together at the same time when you're setting the objective. But again, using symbolic math, we're able to add quadratic models together very easily. So it's still an easy thing to do. Next, we'll add the constraints to the CQM. So we've seen these before in the previous slides. We walked through each of these constraints. The first one is the maximum capacity constraint, and we'll use the add constraint function. Note that I'm not defining the constraint separately. I'm just putting the constraint directly into the add constraint function. So that's a possibility. I'm also labeling the constraints here. So I'm labeling the first constraint, max capacity, and the second one, max parcels. This is recommended so that it's easier to track what constraints you have in the model and access information about each constraint from the sample set. If you don't label the constraints, just a random string will be generated. So it's hard to parse out what the constraint actually is from a random string. So this, yeah, again, this label is recommended. To solve the CQM, I need to instantiate the LEAP hybrid CQM sampler, and then I can pass the CQM to the sampler using the sample CQM function. Note that the only tunable parameter that we provide for the CQM solver is the exact same as the BQM and DQM solvers, and that is the time limit. The default time for small problems is 5 seconds, but we can increase that as needed. All right, so now I'll take a quick look at what we can expect to see when the CQM solver returns a result. So I mentioned that the CQM solver will return the best solution that it found, as well as the intermediary solutions. So you'll see here that we have that each row represents one distinct solution from the CQM solver. We also have this energy column, which is typical in all of our sample sets. Note that for the CQM solver, though, we only use the objective function to calculate the energy. We also have the number of occurrences after that. And then we have two new columns, is satisfied and is feasible. So for each solution that we provide, we're going to get an array back that has the satisfaction status of each constraint. So in our example, we only have 2 constraints. So is satisfied will contain 2 entries to tell us the status of each constraint for each solution that we receive. The last column is the solution feasibility. So in order for the solution to be considered feasible, all of the constraints need to be satisfied. So you'll see that the first few low energy solutions are not feasible, but the remaining 3 are. We'll take a closer look at that. All right, so you did see that in the sample set, actually, I'll go back for a moment. The samples in the sample set are reported in, or are ordered, I should say, in terms of lowest energy. So the first sample returned here has the lowest energy of -3, but it's not feasible. So if you wanted to get the lowest energy feasible solution, the way we recommend is through using itertools and the filter false function. So this is how you would get the first feasible solution. If you wanted to get the first infeasible solution, so the lowest energy solution, and you wanted to understand which constraints were satisfied and which weren't, then again, you can use the itertools filter false function to kind of parse through the infeasible solutions. And then by using is satisfied, as is shown below, you can actually see the satisfaction status, I would say, of each constraint. So in the example that we're looking at and the sample set that was shown above, for the lowest energy solution, the maximum capacity constraint was satisfied, but the maximum parcel constraint was not. So that's why that solution was reported as infeasible. All right, so now let's take a look at this, the code for this. I'm going to share my screen. One moment. All right. So I think you see the Leap IDE with some code in it now. I'm going to just scroll down here. There's a description of the problem at the top, but I want to start with the import statements. So notice from line 32 and line 33, I'm importing the tools I need from Ocean. So the constrained quadratic model lives in DIMOD. If you prefer to use the shorthand, you can just import CQM directly like that, so you don't have to type out the full constrained quadratic model. Both work just as well. The binary and integer objects and constructors also live in DIMOD, as does QuickSum. The LEAP hybrid CQM sampler lives in D-Wave system, the same as the other hybrid samplers. So to start, we're just setting up the problem. I'm going to consider a total of 300 packages, and I want to down select 100 packages. In lines 42, 45, and 48, I'm just randomly assigning a priority to each package. So note that the higher the number, the higher the priority. I'm randomly assigning a number of days that have passed since the package was ordered, so in the range of 0 to 3. And then I'm also randomly assigning a weight or a cost to each package, so between 1 and 100 pounds. The maximum weight, as you can see, is 300 pounds. Okay. If I scroll down a little bit, I've also defined the weights for the objective functions in line 55 and 56. Notice here, I just set them to 1. I want to consider both objectives equally. I'm not going to prioritize one or the other, but depending on your application, you may want to express that differently. And then after that, there we go. After that, I define the CQM, the binary variables. I build out the 2 objectives and add it to the CQM. So I'm going through this quickly because we've already seen this code. I just want to show you what it looks like in the script. Next, we're adding the constraints. Oops. And then from line 38 on, we're instantiating the sampler and submitting our CQM to the sampler. So I'm going to run this now. So we can see the sampler in action, and we can take a look at the results that come back from it. Okay. So in addition to printing out some information about the problem and solution, at the top here, I also printed out the information that's returned with each sample set. So notice here that we have the constraint labels. So you can see from the sample set info what constraints you've added to this model. So what constraints are represented in the model. And then we also show the QPU access time, the charge time, the runtime, etc. So the same as the other hybrid solvers. I'm showing here the distribution of the packages. So in terms of their prioritization and the number of days that have passed since the order was placed. So you'll see we have, for example, out of the 300 packages that we're considering, we had 29 that were ordered 3 days ago and are high priority. So what we want is to make sure that the CQM solver was selecting packages along the first row and the first column. We're really just in this upper, the upper left-hand corner of the matrix here, or the table. And what we see in the solution is that that is indeed what happened. So we selected 27 of the 29 packages that have been in transit for the longest and are also the highest priority. And then we also select a larger number of packages in the upper left. The total number of selected items were 100. So if you add up all of the numbers in this table here for the solution, then you'll get 100. And the solver actually filled up the entire truck in terms of the weight capacity as well. So the total weight of the packages came in at exactly 3,000 pounds, which is printed out here. Okay, I'm going to stop sharing now and go back to the slides. All right. Okay, so in summary, we saw or were reminded that the CQM solver supports binary and integer variables. I just showed an example that uses binary variables, but we have examples on LEAP that also use integer. We saw how easy it is to add equality and inequality constraints now to CQMs. The CQM handles linear and quadratic objectives and constraints. We only worked with linear, but again, on LEAP, we have examples that use quadratic objectives and constraints as well. And we also got to see how easy it is to use symbolic math to intuitively express our objectives and constraints. All right, if you're interested in exploring the CQM solver in more detail, check out our Ocean documentation. We have information on the CQM, the model and the solver, as well as symbolic math. And we currently have 3 code examples available online that use the CQM solver as well. So the distributed computing example, knapsack, and job shop scheduling. All right. So thanks everyone for sticking around for this tutorial. Can open it up for questions now if there are any.
Great. Well, thank you, Alex, very much. And we've got some questions here, and perhaps Victoria, if you want to answer as well, you can unmute yourself. We'll see. So the first question, Alex, how do I know when I should use a CQM and when I should use the linear inequality constraints from Victoria's talk?
That's a really good question. So from internal benchmarking, what we found is that the CQM solver really is the best choice for constrained models. So if you have a number of constraints, it's best to use the CQM solver. Also, I'm not sure, now that we have the CQM solver and now that it has automatic Lagrange parameter tuning, I'm not sure that I personally would want to go through the pain of needing to tune the Lagrange parameters themselves. So I'm probably more biased to just using the CQM solver. Victoria, though, do you have a different perspective on that?
I think the only thing that I would add is that the CQM solver has those functions built in for the quadratic equality and quadratic inequality constraints as well, which I don't think we have in the binary quadratic model package right now.
Okay, thanks. If anyone has any questions, feel free to put them in the chat. I know we've been answering many of them as we go. I'm going to go back and read out a couple of them to get Alex and Victoria's take on it. Here's one. When selecting the D-Wave 2000Q or Advantage, is there any possibility that the 2000Q would produce better solutions for a certain problem because the problem is more suitable with a chimera graph?
Yeah, that's a good question. I think the chimera graph is a subgraph of Pegasus. So one of the key differences between the 2000Q and the Advantage processors is that the 2000Q is a low noise processor. So it has a different fabrication stack or process compared to Advantage. So there may be some benefits on that. But when embedding problems on the 2000Q, they're going to require a longer chain strength. And that's one of the advantages of using Advantage or the Pegasus processor or layout. We can reduce the chain strength, so increase the size of problem that we can fit. And with the performance update, so Advantage System 4.1 now that's in LEAP, that's getting closer to that low noise 2000Q processor as well in terms of noise. Victoria,
Okay.
Could you add anything?
No, I think that was a great answer.
Okay, well, we have other questions coming in. Is there a way to handle non-binary variables?
I've been answering them, so Victoria, you can take this one.
Yeah, so I mean, with our 2 latest hybrid solvers, so the constrained, the CQM hybrid solver, you can have integer variables. And then with the discrete hybrid solver, the DQM solver, you can have discrete variables. So those both give you alternative formulations that you can use and different types of variables. There are ways to kind of implement other variable types using those. So not really built exactly for like continuous, and it might not be a great fit, but there's ways you can kind of discretize those variables and kind of bin the value ranges and things like that to handle it if you need to.
Okay, next question. Is it possible to force a CQM solver to use only the QPU?
To use only, so not to use the classical?
Sure.
No, the CQM solver is a hybrid solver, and so it does use classical resources plus the QPU. It's all kind of built into the workflow. So there's no way to only use the QPU with that.
Okay. If someone could explain again about the strategy to ensure finding optimal solutions, now it just popped up here, for all solved problems, it would be appreciated. Will it be possible somehow only finding good but not optimal ones?
Yeah, it's definitely possible. Like Victoria mentioned before, we don't provide a certificate of optimality. So evaluating whether a solution is optimal or not really does fall on the user. The system is probabilistic, as are the hybrid solvers, and so it's definitely possible to get like good quality solutions that aren't the optimal.
Okay. Do you have an example in the D-Wave docs or demos that shows how to do a model that has some floating point variables in addition to binary and integer variables?
I don't think so, but that sounds like a good feature request. Victoria, do you know if we have any examples like that?
The only one that might could be QBoost, where it's looking at weighting. So that's a classification. It's an ensemble method classifier algorithm. And so it has different decision trees in there, and the QPU is being used for weighting on those decision trees. So that's using that kind of like discretization and binning method that I mentioned. And I believe there's like a paper referenced on that code example where you can look at how they're formulating that using binary variables. But it is, I think, that one's one of our older examples. So it's there, but it may or may not be the most efficient way to solve those problems these days.
Okay, going back to the example you showed, how do you identify which package to pack in the truck?
Yeah, so the CQM solver was considering the priority, the number of days that have passed since the package was placed, as well as the weight of that package. So by considering a combination of all of those kind of characteristics of each package, as well as all of the packages that it could consider, it chooses this best set of packages that satisfies the constraints of choosing 100 packages for the truck and making sure that it isn't, that the total weight doesn't exceed 3,000 pounds, and gives higher priority to the packages that have a high priority shipping status, or that have been in transit for the longest. So it's a number of factors really that go into deciding which packages to load and which to leave behind.
Okay, next question. Any plans to show D-Wave examples on sampling problems like Boltzmann distribution sampling using quantum Boltzmann machines like generative models?
That is on the list of code examples that we're thinking about publishing. Yeah, that is one that we're thinking about.
Okay. Have you implemented a 3D version of this problem?
No, but I know that that is a problem of interest. I think even to some people who may be here today. I believe there's a 3D bin packing paper, though maybe I'm making that up. There are folks at D-Wave who've done some work on that. So if anyone is interested, feel free to reach out to me or to sales, and we can connect you with the right information on that.
Okay, well, I know there's some other questions in the chat, but we do have people who will go through and answer that. It just takes a while. So why don't we just move on to the next section? And again, we will get to your questions in the chat. And when Victoria is done with the next part of the tutorials, we will come back and have a final Q&A session. So thanks very much, Alex. Thanks, Victoria.
So we are here to talk about using NumPy for large quadratic models. All right, so again, I'm Victoria Galieber. It's really nice to meet you all again virtually. So in this talk, we're going to assume that you have been using our quadratic models in the past, that you're somewhat familiar with, formulating problems as a binary quadratic model. But one of the things I've been hearing in my time in the field, both in sales and in customer training and customer support, is once people start scaling up to larger, real world size problems, there's some classical bottlenecks in how they are building up their binary quadratic models. So even before you send your problem over to a hybrid solver or the quantum computer, there may be more efficient ways that you can structure your Python program. Python, it's known for being, a little bit slow, but there are some really efficient packages like NumPy, which is the one that we're going to talk about today, that you can use to really speed up those classical portions of your programs. So, as Alex mentioned, so we have our 3 hybrid solvers. We have our binary, our discrete, and now our constrained quadratic model hybrid solvers. And for some of these bulk-sized solvers, you can run problems for binary up to 1 million binary variables, discrete up to 5,000 discrete variables, and now with the CQM up to 500,000 variables on our bulk solvers. So these are huge problems. These are huge data structures that if you build things up using, for loops and you do things kind of in a naive approach, it can be very slow, and those classical parts of your program can be really time consuming. So it can really be a bottleneck. And so it's something to really keep in mind as you start scaling up to these larger quadratic models. So this is where we're going to talk about NumPy. So what is NumPy? A lot of people that use Python are very familiar with NumPy because it's really useful for performing array operations very quickly. So NumPy uses vectorization. What this means is that you're not going to have for loops or anything like that. These are going to take place behind the scenes, and it's going to be running C under the hood. This is how it's going to get some of those speedups and some of those efficiencies. NumPy also uses broadcasting, which is where you can broadcast element by element operations over an array or a matrix. You can use slicing to do this broadcasting over submatrices and subarrays. NumPy has a lot of mathematical operations for working with arrays like vectors and matrices. And so this can make your code a lot more compact, and it can more closely resemble mathematical notation when you can just reference these mathematical operations. So just to review really quickly, so this binary quadratic model, this is what I talked about in that first hour, where we have these linear and these quadratic terms. And what we as the programmer have control over are these A's and B's, these coefficients or biases. And then the quantum computer or our hybrid solver is going to return back the values for these Q's, the zeros and ones that tell me how to minimize my objective. So again, we have a linear bias on qubits, and we have a quadratic, this bias on the couplers that pair together pairs of qubits. Now, what some of you may be familiar with if you've been using Ocean for a while is thinking about these coefficients and storing them in a matrix. So you can build up a Q dictionary or a matrix, and you can store these coefficients in this way, where you have the linear coefficients along the diagonal, and you have the quadratic coefficients on the off diagonal. Now you'll notice in my matrix, I've only put these quadratic coefficients on the upper triangular portion. It really doesn't matter if you put them above or below the diagonal. The main thing is that you don't want to put them in both places. So just each coefficient goes either in Bij or Bji, but not in both. And so what we see is these linear ones along the diagonal And like I mentioned, we can think about this as an upper triangular matrix where we have all of these quadratic terms above the diagonal. All right, so let's dive right in and see how we can use NumPy to transform and make some of our code more efficient. We're going to go through two examples. One will be a simpler example that we'll start with, and then we'll dive into a more complex one where we're really going to get down in the weeds a little bit. So the first one we're going to look at is the number partitioning problem. For any of you that have taken one of our training courses recently, I'm sure you're very familiar with this problem. All right, so the number partitioning problem, you're given a list of numbers. We're going to call that list S. It's just a list of different numbers. And what we want is to partition this list into two lists that have equal sums. We don't care how many are in each sublist. We just want the sums to be equal. Now, if you go through the binary quadratic model formulation of this, you end up with a cubo or a binary quadratic model that looks like this objective here. So you can see I've done all of the math and all of the simplification to combine everything together into one math expression here. And this is where we have our linear and our quadratic terms. So in this expression, the x's, those are our binary variables. The s's, those are entries in our list of numbers. And c is a constant number, which is actually the sum of all of the numbers in the list. Now, this cubo, if you run it on the quantum computer, you should get back a nice partition of your list with equal sums. This problem, it only has an objective where you're trying to minimize the difference between the two sums. There are no constraints or anything for this problem. Now, one of the ways that we like to go through this and in a really clear way that's easy to understand is to do this with for loops, where we build in those linear coefficients and those quadratic coefficients right into a matrix form. So in this code snippet that you see here, that first, the linear summation, where I have the single sigma, the single summation, that's my first for loop. So for I going from 1 to n, that's going through all of the entries in S. And then on the linear, the diagonal entries in that matrix, so you can see Q, I, that's like row I, column I. I'm adding in my linear coefficient, this negative 4CSI plus 4SI squared. That's my linear coefficient going on the diagonals of my matrix. Now for the second summation, we've got a double summation there for our quadratic term. So we have a nested for loop here, where our second summation ranges from I plus 1 to n, the length of S. And here for those off diagonal terms in row I, column J, I'm adding in 8 SI, SJ as my quadratic coefficient. So for a small problem, this is a totally fine way to build up your Q matrix that you can then submit to the quantum computer or to our binary hybrid solver. Once this gets big, though, you can see we have a nested for loop here where we're running through n things in each of these loops. So it's not super efficient. And this is one that we can run a lot more efficiently with NumPy. So let's see how we can do that. So the idea is that we're going to build up this matrix of those linear terms along the diagonal and the quadratic terms above the diagonal using matrix operations. So the first thing that I'm going to do is that list S of numbers, I'm going to think about that as a one-dimensional vector. And now going back to your high school math where you did your matrix multiplication and everything, if I multiply these two vectors out, I'm going to get a matrix that's n by n, where in row I, column J, I'm going to have SI times SJ. And so in this way, I can really get my hands on that quadratic coefficient. So I can do this with NumPy to build up that quadratic bias, which was 8 times SI, SJ, just by using NumPy operations. So here, S and P dot reshape, that's me basically taking my list S and looking at it as a one-dimensional vector. You can see I have the first one is just my vector S as is. And my second one, I'm multiplying it by 8 to get that 8 SI, SJ for every entry in my matrix. And I'm just going to use NumPy's multiply function to do this really, really quickly and in this one line rather than those nested for loops. So now we have a matrix where everything is filled in with 8 times SI times SJ. But we didn't need the whole matrix filled in. Remember, I said in the beginning that we only want the part above the diagonal filled in. We don't want those entries in both places. Now, NumPy has a function for that as well. NumPy's tri-U, so upper triangular. I'm going to take this matrix Q that I just built, where every entry is 8 SI SJ. And I'm going to say I basically want it to put everything that's in the diagonal or below the diagonal, set that equal to 0. And what I'm going to be left with is a matrix that's all zeros. And then above the diagonal, it's filled in with 8 SI SJ, just like I want for that Cubo matrix. Now for the linear bias, we had a coefficient of -4c times SI plus 4 SI squared. Now, again, we can just use our one-dimensional vector of S. And if we use NumPy to build up a vector for that diagonal, all of these entries that we want on the diagonal, I can just do -4 times C times my one-dimensional vector S. So then everything in there is going to be multiplied by -4 times C. I'm broadcasting that across the whole vector. And then I'm going to also add 4 times this S vector squared. And when I do squared like this in NumPy, it's going to square entries element-wise. So this is going to be filled with, S0 squared, S1 squared, S2 squared, and so on in there. And so I've now built up a vector that has all of my diagonal entries that I want for all of those linear coefficients. And again, I've done that in one line without any for loops. Now NumPy has a function that's called fill diagonal, which we'll use here. And so we'll give it our Q matrix that we've filled in so far, where everything on the diagonal and below is 0. And then I'm just going to put that diagonal vector right along the diagonal. And now when I've done that, I have this Q matrix that consists of my linear coefficients along the diagonal and my quadratic coefficients above the diagonal. And I'm going to use this to build a binary quadratic model. I'm just going to say binary quadratic model, give it my NumPy matrix that I've built called Q, and say I'm going to use binary variables. Now, one thing that I want to be really careful to mention here is that there are a couple different ways to build your binary quadratic model from NumPy structures. Now, I'm going ahead and doing it this way because it's the first example. I want to do it the simplest way, but also it's a very dense matrix. So every entry in my matrix on the diagonal and above is filled in. So what that means is that I have a dense problem. And so this is really only going to be efficient because this problem is dense. And so for sparser problems, we're going to use the NumPy vectors method that I'm going to show you next. But essentially, you can get started just this way. You can build it up. You can make sure that it matches the BQM that you've built in, the for loop method in your code, and you can make sure that everything is working as expected, and then take advantage of those speed benefits. Now, when I took this problem and I gave lists of random numbers where along the x-axis, you see the problem size. So the original problem that I worked with, the list S only had 8 numbers in it. But if I let S just be random numbers ranging from 1 up to 1,000, and I compared the runtime for just this classical portion of my Python program, building the binary quadratic model. This does not include sending it over to any solver or anything, just that classical work of building a binary quadratic model. You can see that there's massive speedups here to be had using NumPy. So once you start scaling up to these larger problems and you think about how our hybrid solvers, that binary one can run problems up to 1 million variables. You're going to want to be really smart and really efficient in how you're building up these binary quadratic models so that you don't have any of those bottlenecks. All right, so that was kind of our intro example. So now we're going to really dive into one that's quite a bit more complicated. So example 2, we're going to go through the electric vehicle charger placement. This has been in our collection of examples for a little while now, I think actually almost a year. And this problem, the setup, so basically we have a list of potential charger locations on a map. We have a list of existing charger locations on a map, and we have a list of points of interest. And what we want is the system to return to us, where should I build my new chargers? Which of those potential electric vehicle charger locations should I build in? And what we want to take into account is we want to minimize the average distance from the new chargers to the points of interest. We want to minimize, we want to maximize the average distance from new chargers to existing chargers. So we don't want to build a new charger right next to an existing one. And then we also want to maximize average distance between new chargers. It doesn't make sense to build 2 new chargers right next to each other. And then we're also going to have some constraint to choose a fixed number of new chargers. So I believe in this example, we're just going to do 2 new chargers. So there's a lot of different things going on. We've got several different things to minimize and maximize. We've got a constraint on the number of new chargers. So what we're going to look at in this talk is just one of these and how we can formulate that. So we're going to focus in on this first one. How can we formulate this objective to minimize the average distance from potential charger locations and any new chargers we're building so that it's a minimized average distance to our points of interest? How can we use NumPy to formulate this constraint? So let's see what we're actually looking for. So in this picture on the left, you see a current map of the situation. So this is a map where all of the black space is where you could build a new charger. The red circles are where there are existing chargers, and the P's are points of interest. Now, the map on the right is what we would do in the future. This is the output of the system that we're looking for. You see these blue dots, the blue circles, and that's really where we should build those new chargers. So you can see on this map that we're placing the new chargers kind of right in the middle where there's a gap, but we're relatively close to the points of interest. We're not way on the edge of the map, but we're also not right next to each other and not right next to existing chargers. So this is a fairly good placement in my opinion. All right, so for this first constraint, minimize the average distance from any new chargers to the points of interest. So in the code example, what I've shown here is just the code snippet that's building this up in the current code example. So we have a distance function. It's your standard distance function, just not taking the square root, where you're looking at, x1 minus x2 squared plus y1 minus y2 squared, if you're finding the distance between 2 points. Here the points are A and B, where the first entry is the x coordinate and the second entry is the y coordinate. Then to build up our objective here, this constraint, we're going to use a for loop where we're looking at each potential new location. We're going to compute the average distance from that location to all of the points of interest. And we're going to bump up that linear coefficient by that average distance times some Lagrange parameter. All right, so we want to minimize average distance. And so we're going to penalize it by average distance. And since the system is going to minimize, it's going to try and pick out the ones that have smaller average distance. So this is what the current code looks like. We've got a for loop here. It's just one for loop, so it's not too bad. But what you do see here is that it's going through all of the potential new charging locations. And so remember in that picture on the last slide, I said all of that black space was potential new charging locations. So that could be a lot of new variables to go through. So let's see if we can do this more efficiently. All right. So basically what we're doing, just to summarize the mathematics, because that's how we're going to build up the NumPy operations, is we're computing the average distance from one new charger to all points of interest. We're going to do that by computing each distance individually. So from the new charger to each points of interest, add those distances all up, and then divide by the total number of points of interest. And that's going to give us an average. Then we increase the linear bias by this average distance with some Lagrange parameter. And we do that in that for loop for every new charger. So let's look at doing this using matrices now. These 2 blue columns, the first one is the x coordinate. The second one is the y coordinate. And we've got a row for each new charger location, each of those potential locations. So we just have, 2 columns and then a row for every new charger. Similarly, for the points of interest, we have 2 columns, the first one being the x coordinate, the second one's the y coordinate, and we've got a row for each point of interest. So on the map that we saw before, for the blue one, that would be like all of the black space, all of the potential new charger locations. And for the orange one here, for the points of interest, that was like those 3 P's that you saw scattered around, so a much smaller number. We're going to build these arrays and use these to build up our constraint. So that formula for computing the distance, here I'm using subscript C for charger and subscript P for point of interest. So if that formula that was in the code, this first line formula, that's exactly how it was written. I did the X for the charger minus X for the point of interest squared. When you square that out, you get this polynomial, and same for the Y's. Now I'm just going to rearrange that a little bit so that I can see how I can get a handle on this stuff a little bit easier with these matrix operations. So I put the X for the charger and the Y for the charger where they're squared and they're kind of on their own. I put those in one set of parentheses. I did the same thing for the points of interest. You know, I put those X and the Y's, they're both squared, put those in one set of parentheses. And then these cross terms, these quadratic terms, I'm going to put those in the last set of parentheses there. And they both have a coefficient of -2. So let's go through this term by term and see what we can do with these matrices that we've built up to construct these sums. So the first term where we're just summing up the X coordinate squared plus the Y coordinate squared for each new charger. Remember, we have this blue matrix that we built up. So basically, if I square every entry in this matrix element wise, I'm going to have all of the X's squared and all of the Y's squared. Then I have a row for each new charger. And so if I just add up across the rows, I'm going to get x1 squared plus y1 squared, x2 squared plus y2 squared. And I'm going to get exactly those sums that I need for each new charger. I'm now going to have this vector where there's one column and a row for each new charger. And it's going to be filled in with that first term that I need to get a handle on. Now I can do the second term exactly the same way with the point of interest array. So again, I can use the same process. I'm going to square everything element-wise and then add up across the rows. And I'm going to get x squared plus y squared, a row for each point of interest. So that's how I can compute those first two terms using matrix operations. Now, what about this cross term, this last term where we have -2 xcxp plus ycyp? How can I get those with these blue and orange matrices and vectors that I now have at my disposal? Well, what I can do is I can multiply these together. So if you think about your matrix multiplication, so again, going back to a matrix multiplication where you go, across the row, down the column, if I multiply both of these, the original ones with 2 columns, then what I'm going to get is this big teal matrix on the right, where I'm going to have a column for each point of interest, and I'm going to have a row for each new charger. And in row C, column P, I'm going to have the x coordinates multiplied together plus the y coordinates multiplied together. So I'm going to have in this matrix exactly those terms that I need for that last term. It's not going to be multiplied by -2, but that's really easy to take care of later. But at least here, I've now got a handle on everything inside those parentheses that I need to compute with the matrix operations. So now I've figured out how to do basically all of this distance formula using matrix operations. So combining everything together, I'm going to multiply that cross matrix by -2. And then I'm going to add in those squared sums along the rows for the chargers and the columns for the points of interest. So let's see what that looks like. So as a visual graphic, so I've got the teal matrix where there's a column for each point of interest, a row for each new charger. And I'm going to take these squared sums for the chargers and I'm going to add that on every single column going right across my matrix. And then my orange or yellow row that I have down at the bottom where I have a column for each point of interest for that squared sum, I'm going to add that to every single row, just moving my way up that matrix. And what I'm going to be left with is this purple matrix where row C, column P equals exactly that distance equation that I was trying to compute. And I've done this all with those matrix operations, which means that I can use NumPy to do it really fast. All right, so now what we just have these distances. So we have distances from all new chargers, so from every new charger to every point of interest. We need an average from every charger an average to all points of interest. So how are we going to do that? We're going to sum across every row. We have a row for each charger, sum across each row, and then divide by the number of points of interest that we have. That was an input to the problem. We knew for the example plot that I showed you, there were 3. So that's just a constant number. So now when I do that, I'll be left with just one vector, one column, where in this column, row C is going to equal the average distance from charger C to all points of interest. And that's how I'm going to get a handle on that linear coefficient using matrix operations. Sounds like a lot of work, and it sounds way more complicated than what we did in the original code snippet, but I promise you it'll be much faster. So here's a summary of all of the steps that we went through. We went through a lot of steps. So first we built those XY arrays, one for the new chargers and one for the points of interest. Then we built those squared sum vectors. We squared entries element-wise, and we added across the rows, both for the new chargers and the points of interest. Then we built that cross-term matrix using matrix multiplication. We just multiplied those 2 matrices that we had, and then multiplied that matrix element-wise by -2 to get that -2 coefficient. What we did next was we add those squares, the squared sum vectors, to that big cross-term matrix we computed. And from that, we were able to get that vector of the average distances, and that's going to be the diagonal entries for our cubo so far, for this constraint. All right, so let's go through how you do this using NumPy for each of these steps. So the first step, we built those XY arrays for new chargers and points of interest. Basically, I'm just going to create a NumPy array. These original inputs, this potential new charging station nodes and points of interest, these were 2D lists where each item in the list was basically a tuple of an X coordinate and a Y coordinate. So I can just read those right in through NumPy and get them back as a NumPy array, or this matrix that we're looking for. Next, we built those squared sum vectors. So we squared entries element-wise and added across the rows. So what you see here is for my potential new charging stations squared. I'm going to, inside parentheses, first square everything element-wise. And then I'm going to sum across the rows. That's what this axis equals 1 is saying. It's saying sum across the rows. And I'm going to do the same thing for this points of interest squared. I'm going to square everything element-wise and then sum up across the rows. Again, you'll notice that there's no for loops here. So we're using NumPy for all of these operations. So that's how we know we're going to get those speed savings. Next, we have to build that cross-term matrix. So that was just regular old matrix multiplication. And then we wanted to multiply that element-wise by -2. So I'm going to just say, NumPy, give me some matrix multiplication of my potential new charging stations, NumPy array, my point of interest array, turn it on its side. So that's a transpose there. And then that -2 out front, that's going to multiply everything element-wise by -2. And we're going to save that in this CT matrix for this cross-term matrix. All right, then the next step, so we add those squared sum vectors to the cross-term matrix. So remember, we wanted to add the new chargers vector to each row, and the point of interest vector adds to each column. So you're going to have to reshape one of these, and the other one will be in the right shape. So you can just usually look at like the dimensions of your matrix to figure out which is which. And here we're just adding that to what we have in our matrix. All right, and then our last 2 steps. So we now have our cross-term matrix and everything, and we need to sum across the rows for the total distances, and then divide by that constant number, the number of points of interest element-wise for an average. So you see here, I'm summing across the rows for the total distances for each charger, and then this division by num POI, that's going to be element-wise to give me that average distance. So this is going to be that vector where it's one column and each row is going to be the average distance from that charger to all of the points of interest. This is going to be our linear biases for that constraint. And so basically, I'm just going to save that in a vector called linear. I'm going to add that into whatever's there. So probably initialize that with some zeros. And then if this is the first constraint, you just add it right in. If there's other ones in there, you still just add it right in. You just add it to whatever you want. So that's going to be our linear bias right now. All right, so if you want to actually code this up with NumPy, like I said, it sounds like a lot of steps, but you can do it in just these couple of lines of code right here. So I'm going to check that I have more than at least one point of interest before I go through this computation. And I'm going to build up my cross-term matrix, doing that matrix multiplication times -2, those squared term sums you see next on lines 56 and 57. And so that's building up that cross-term matrix. And then in 59, line 59, you see in one step, I'm adding to my linear biases, and I'm doing that sum and dividing by the number of points of interest. So I'm computing that average and multiplying by a Lagrange parameter and adding it to whatever I already have for my linear biases. Now, this code is available in our EV charger placement. We added it fairly recently, so there's now 2 demo Python programs in there, one that runs with the for loops and another that runs much more efficiently with NumPy. So if you want to take a look and see how the other constraints were implemented, you can go and take a look at that there. So completing the binary quadratic model. So we've got other constraints and objectives that we need to add in. So you can handle each of these using NumPy in a similar way. Like I mentioned, they're all in that code there that you can find in our collection of code examples. But then to build the binary quadratic model, we're going to build this one a little bit differently. This one is not a fully dense problem. It doesn't have every single entry in the matrix filled in. So we can more efficiently build our binary quadratic model by using the from NumPy vectors function. Using this function, rather than just giving it the entire matrix, I give it a vector for the linear coefficients. So like that vector that we built up in that last constraint. And then I give it a set of 3 vectors for the quadratic biases. So Q1, that's going to be all of the row indices. Q2, that's all of the column indices. And Q3 is the actual value in the matrix. So in this way, you don't have to store these like massive NumPy matrices if you're not using all of the entries. You can have time and space savings by using this from NumPy vectors method. You can also use it, set and offset, do different types of things that you're familiar with the binary quadratic models. I'm not going to use that here, so I just have offset equals 0. And again, like I mentioned, this is just the row column bias. Takes a little to get used to, but much more space efficient than storing the entire matrix. All right, so when I ran this, so with this electric vehicle charger placement code example, there's an option to input the size of the map. So how big is that grid where you're choosing where to put your chargers? So by varying that problem size, you can see some of the cost savings on this plot. Looks pretty similar to the number partitioning scale plot. But what I want to point out is that this runtime on the y-axis in seconds, this is much, much longer. So if you looked at this on the number partitioning problem y-axis, it only went up to maybe like 3.5 seconds, whereas this one is going up to 50 seconds to run a problem with 2,500 binary variables. So again, just think of the cost savings that you can have, the time savings in building up your binary quadratic model by using NumPy rather than using those for loops as your problem gets large. All right, so now I'm going to go over and share my screen, and we'll take a look at the code and look at some of the cost savings. All right, so you should all be able to see my screen now. There we go. And what I have open here is the D-Wave Examples electric vehicle charger placement code example. In this code example, this looks really similar to the picture that I showed you on the slides of the problem setup. And again, there's a little bit of information on customizing the scenario. So you can change the problem size by changing the size of the map where you're placing chargers. There's more information on the problem formulation. So if you're interested in how those constraints are actually formulated with the binary variables. And then there's even a little snippet here about the faster BQM construction with a very familiar looking plot now that you just saw on my last slide. So let's take a look. So in the code, again, I can make this a little bit bigger for you all. And so this is the standard code, right? So this is the code example where we're going to build up. I'm just going to scroll down to this build BQM function where we're actually building the binary quadratic model. And you can see, constraint 1, we've got a for loop here. Constraint 2, we've got a for loop here. Constraint 3, we've got a nested for loop here. So that's going to be really expensive. And then constraint 4 is using DIMOD generator's combination function to choose exactly 2 new charger locations. And this is actually fairly efficient. This function is using NumPy under the hood. So that one's pretty nice there. So if you run this demo, it will run beautifully. You'll get a nice picture and output on the scenario. But what we also have in the repository is this demo NumPy. And if you go to demo NumPy, you see basically only this build BQM function. We're going to use all the other functions from the original demo file. The only one that we're really modifying is this build BQM. And this is going to be built up now using NumPy in an efficient manner. So here you can see constraint 1. There's no for loops now, right? So this is using NumPy. This is the one that we already discussed, where we're building up this cross-term matrix of the distances with the matrix multiplication, and then summing the 2 squared terms, and then computing the average and adding it to the linear bias. Constraint 2, you'll see a similar thing where we're looking at maximizing distance to existing chargers. We've got matrix multiplication, sum, and then computing an average. Now we're maximizing instead of minimizing, so there's a -1 there. Constraint 3, this was the one that had the double for loop in here. And this one, again, we've been able to do this in one line by building up a distance matrix here for comparing the current charging location to other new charging locations. We've got a little else statement in case we're only asking for one, then it's kind of irrelevant to compute that. And then what you see here is this constraint 4. I've shown how to do it explicitly using NumPy rather than combinations function. But like I mentioned, the combinations function is pretty efficient. You'll see here how I built up these Q vectors that I need for the row indices, the column indices, and the bias. This is not really the most efficient way. I did actually build up an entire matrix and then just pull those out. So not really the most efficient way, but wanted to make sure that you all saw how you can use that as an input. But yeah, feel free if you want to make this even more efficient. We're definitely open for pull requests, so you could try that out. All right, so let's go ahead and run these and compare the runtime. Now, I've modified these files a little bit so that we can compute the runtime of building the binary quadratic model. So I'm just surrounding the build BQM function with the time function. And I'm not even going to run it on the hybrid solver service or anything. I just want to look at what is the time, the classical compute time to build up my binary quadratic model. And I'm going to have the same thing here in my original demo file. Again, I'm going to compute the time just for building up the binary quadratic model. And then we'll see what that looks like at the end. So let's run this and let's see how much time this takes to build up the BQM using for loops for this problem. So this is pretty quick. I mean, it's not a huge problem. I think the grid is like 10 by 15. So not a massive problem, 0.085 for our runtime. Now let's go over to the NumPy function and run that and see what we get. Again, not a huge problem, but look at those cost savings already, right? So much, much faster using the NumPy method. Like I mentioned, this is a small problem, so not too much in the savings that you'd really notice. But as you scale up to those larger problems, do you want to be spending minutes waiting for your BQM to be constructed classically before you're even sending it over to the hybrid solver? So really taking a look at how you can do this efficiently is going to make your problems run much, much faster and avoid some of those classical bottlenecks. All right, so if we go back to the slides, then we can just wrap this up. All right. My clicker seems to not work. All right, there we go. So for more information, I've just got a link here to NumPy, so you can go and look at their documentation and some of their examples, so you can really start learning how to use NumPy. We've also got our ocean documentations where you can look at that function from NumPy vectors and see some code snippets on using that. And then last but not least, again, this code example is freely available to the public on GitHub. You can get there either through Leap on the resources tab. You can find it in our collection of code examples, or there's a direct link here. So it's github.com/dwaveexamples/EV charger placement. All right. So with that, are there any questions?
Thank you, Victoria. We've again had lots of questions in the chat. Before we go to the final questions, I would just again like to thank everyone for coming to the conference. I hope you were able to spend time, not just today, but the previous 2 days. We're uploading as quickly as we can the videos that we recorded from the past couple of days. So hopefully by the end of day tomorrow, you can go back and watch any sessions that you missed. It will be available in the Pathable platform for up to 3 months. And then we will also be posting them to the D-Wave YouTube channel. And speaking of the D-Wave YouTube channel, for additional resources and information, we have lots of webinars that we've done, both Programming 101 as well as introductions to Ocean and lots of other information available on demand on our YouTube channel. So take a look there. We continue to do webinars about once a month, so make sure you're on our mailing list so you get notified about them. They're always very popular. Lastly, again, before the questions, I posted in the chat a link to a survey. I know people really don't like filling out surveys, but we really, really hope that you will. We're trying to make this conference more valuable every year, and we would like to get your input before we start planning the session next year. So take a look in the chat and the link is there. Okay, so that's my commercial. We'll go on to the questions that remain here. How do you impose all the elements from a set in a binary quadratic model?
I'm not sure I fully understand that. Can we get some clarification on what you mean by impose all of the elements in a
well,
set?
Valerio, if you would put your question back in the chat again, that was great. That would be good. A question related to how to integrate with the C++ code software.
So basically our Ocean SDK is Python. So you're going to want to look for different packages that are going to be running C under the hood, or different ways that like just standard Python has to integrate and work with C. So one of those, like NumPy under the hood, it's C. So I'm sure there's other packages as well that you can use to kind of work together with some of the more efficient tools that are available in C and C++.
Okay. Can this matrix formulation trick be applied to CQM as well?
Alex, do you want to answer that one?
You can go for it. I feel like you have more experience in this domain.
So I don't believe so, unless, I feel, so the advantage of CQM is that you can just leave your constraints as these equalities and inequalities. So for the CQM solver, I would trust that our software team is making these functions efficient and improving efficiencies over time. So I wouldn't be too worried about it. It's more really for those binary problems, like Alex mentioned in her talk, where the binary quadratic model, you have up to 1 million variables. And so those are like huge problems. And while you can model things as a discrete quadratic model or a constrained quadratic model, those have the fewer variable counts because under the hood in the software, there's some conversion taking place for you. So it's mostly relevant to the binary one. You can tune some of the, you can do like linear and quadratic biases directly with the discrete quadratic model. But I don't think unless you just put everything in the objective for CQM that you would be able to do that. And then you're kind of losing the benefits of CQM by having the constraints spelled out separately. Alex, what do you think?
Yeah, I handed the question over to you because I was trying to imagine how you would do that with the CQM. But I agree with what you said. I guess you would have to just put everything in the objective. So, yeah.
Okay, so our last question of the entire conference. Do you have an example to use NumPy for the CQM as well?
So I think basically like from what we just said, that it's not a great fit. I would try out the CQM, and if you start running into like those bottlenecks, then I mean you can always submit feature requests on our GitHub on D-Wave Systems where the code is actually implemented for the constrained quadratic model. But I wouldn't worry about it too much, but I don't think that there's any examples that really discuss the efficiency. They're more like educational examples for getting started at this point.
Okay, well, I think we're done for the day. Thank you all so much for coming. Again, please go fill out our survey. We'll love you forever. And we hope to see you all here at Qubits next year. Thanks, everyone. Thanks, Victoria and Alex.
Thank you.
Thank you.